Inside any real atom or molecule, electrons are engaged in a relentless, instantaneous dance. Because they carry the same negative charge, they spend every microsecond rapidly dodging one another in a dense, chaotic, but mathematically bounded choreography. Capturing the exact nature of that choreography is the central challenge of quantum chemistry. For decades, the bedrock of these calculations has been the Hartree-Fock method. Hartree-Fock makes multi-electron systems computable by relying on a specific mathematical shortcut known as the mean field approximation. Instead of tracking the exact position of every single electron relative to every other electron, the mean field approximation simplifies the math. It treats each individual electron as moving through a static, average cloud of all the other electrons. This diagram contrasts theory with reality. On the left, Hartree-Fock models a smooth, average field. On the right, real electrons instantly adjust trajectories to repel each other. Hartree-Fock misses this coordinated spatial avoidance, creating a gap known as electron correlation. To quantify the magnitude of this flaw, physicists rely on the variational principle inherent to Hartree-Fock theory. This diagram illustrates the consequence. Because Hartree-Fock is variational, its calculated energy, the upper line, is consistently higher than the exact true energy at the bottom. The gap between them is the correlation energy, defined mathematically as the true energy minus the Hartree-Fock energy. Because electrons will naturally arrange themselves intelligently to minimize electrostatic repulsion, accounting for this correlation must lower the total energy. Therefore, correlation energy is always a negative value. Without calculating this negative correlation energy, our predictive models sit at an artificially high energy state. Any resulting calculations for molecular stability, key reaction barriers, or bond strengths are physically incomplete. Fixing this requires recognizing that electron correlation operates across two distinct physical realities, requiring two different mathematical solutions. This graphic defines two flavors. On the left, dynamic correlation. This is the short-range, instant-by-instant spatial avoidance between electrons. On the right, static correlation. When long-range effects occur, like stretching a hydrogen molecule, a single Hartree-Fock determinant cannot describe the breakdown into two neutral atoms. The earliest and most brute-force mathematical framework engineered to push past the single determinant limit is called configuration interaction, or CI. This personality map models configuration interaction. It starts with the base Hartree-Fock reference in the center, then linearly mixes in multiple excited configurations. By promoting electrons into virtual orbitals, creating single, double, and triple excitations, the math builds a richer, more flexible wave function. If you include every possible excitation within a chosen basis set, you reach full CI. Full CI provides the exact quantum solution for that basis set, but it carries a significant computational flaw. The top graph illustrates a severe combinatorial explosion. As you add even a few more electrons or orbitals to a system, the number of possible determinants grows exponentially, making full CI physically impossible to compute for anything larger than very small molecules. Chemists attempt to bypass this explosion by truncating the math, intentionally limiting the calculations to only single and double excitations. But this truncation breaks a macroscopic law. Focusing on the scale at the bottom, we see the size consistency problem. If two separated molecules do not interact, the combined system's energy should equal the sum of its parts. Truncated CI violates this test. Because simple linear mixtures either break our computers through combinatorial explosion or break physics through size inconsistency, quantum chemistry requires entirely different mathematical architectures. We must split the toolset. First, we need an architecture dedicated exclusively to strong static correlation, where a single Hartree-Fock starting point is completely wrong. This scale demonstrates a breaking chemical bond. As it stretches, bonding and antibonding configurations become equally important. The solution is CAS-SSCF. It selects an active space of essential orbitals and distributes the active electrons among them in all possible ways. With static correlation solved, we pivot back to dynamic correlation. For this, chemists rely on a highly efficient computational workhorse, Mahler-Plesset perturbation theory, or MP2. This illustration represents MP2 as a wooden scaffold built on a concrete foundation. MP2 treats electron correlation as a small, perturbative correction upon a solid Hartree-Fock base. But if the foundation is compromised by static correlation, the entire MP2 mathematical scaffold collapses. For high-accuracy calculations of single-reference dynamic correlation, the field relies on a different architecture entirely. It is the gold standard of quantum chemistry, coupled cluster. This branching diagram maps the coupled cluster method. Instead of a linear approach, coupled cluster applies an exponential operator. By inputting just single and double excitations, the math automatically generates the required disconnected higher excitations, like quadruples, indefinitely. This automatic generation of higher excitations guarantees size consistency. It delivers the precision that linear CI attempted without violating the physical laws of separated molecules. The computational toolkit is now specialized. CAS-SCSF handles severe static near-degeneracies, while coupled cluster dominates dynamic correlation, providing exact tools for specific molecular realities. Deploying these methods is a rigorous diagnostic process, dictated entirely by the physical parameters of the target molecule. This decision tree starts with one question: are bonds breaking, or are there near-degenerate orbitals? If yes, standard tools fail. Proceed left to CAS-SCSF. If in equilibrium, move right, balancing accuracy against system size. Massive systems go to MP2. For benchmark precision, use coupled cluster. This toolkit summary table maps the compromises researchers make every day. Every method trades computational cost against its capability to handle dynamic or static correlation, while maintaining size consistency. These mathematical choices directly dictate the success or failure of real-world materials science and technological development. The chart's lower quadrants show where multi-reference methods are mandatory. Modeling combustion or transition metal magnetism requires tracking closely spaced configurations. Meanwhile, modern OLED displays rely on dynamic correlation. Predicting precise emission wavelengths requires models that accurately map electron avoidance. The average field approximation provided the foundation of quantum chemistry,